When you have machine learning, you can have a bunch of requirements. Here's the requirements for my car. Cool. And I collected a bunch of data and the machine learning learned whatever it did. Did the machine learning learn what I wanted it to? I don't know. Let's drive it around and find out. And you've lost the causal relationship between the design and the implementation. They're completely unrelated.
ARM is the industry's highest performing and most power efficient compute platform with unmatched scale that touches 100% of the connected global population. Together with the world's largest computing ecosystem and 22 million software developers, ARM is building the future of AI. Hi, my name is Junko Yoshida. I'm the editor-in-chief of Junko's Tech Probe on Substack. And now we are actually studying the series called Domain-Specific AI. What we mean by that is that I think it's high time for AI to just being used as toys to help your homework or do your marketing writing to actual tools that can be effectively used in different domains. And today, we are so honored to have Phil Koopman. He is a professor at Carnegie Mellon University. He's an expert in embedded system software and safety. Hi, Phil.
Hi, Junko. Hi, Ron. Thanks for having me on.
Yeah, and yeah, with me, I have Ron Wilson. He is our technology editor, and I expect him to weigh in, ask hard tech questions. The reason why I actually wanted to pick this topic was I was kind of surprised to hear other industry people who are pushing the use of AI in their own domain. They always look up to the examples of robotaxi or highly automated vehicles. And they always point that out and say, look, Junko, how far we have come. This is why we have to move into this direction, which partly true, but partly not so true. The experts like Phil, who have been involved in robotaxi safety issues for a long time, have plenty of experience in terms of learning lessons and things he has probably discovered that he hadn't thought about before, right? So let's start with you, Phil. The automotive industry, why do they want to use AI? What's the purpose?
The automotive industry uses AI the same way a lot of other folks use it, which is to do things you don't know how to do using conventional software. And the big, compelling application for them is being able to recognize and characterize and predict what other objects on the roadway, what they are, what they're going to do next. And people have been working for decades on how to do that. I mean, there was AI before machine learning, but it was always really hard. And in a conventional software, you'd have to say that is that a person? Well, a person has sort of a round thing on top, maybe some hair, maybe not, maybe a beard, maybe not. And there's some shoulder looking things and maybe some arms most of the time, and trying to tell a computer what a person is really hard. And is the person in a funny hat? Are they wearing a costume? Are they they're halfway behind a tree? It's really hard to sit down and write all the things that make it look like a person. So instead, machine learning came along and it said, well, we don't know how to tell a computer what a person looks like. It's just too hard. So instead, we're going to show it a whole bunch of examples and use statistical approaches to say, well, that thing smells, looks, yeah, it's probably human, right? And so machine learning solved the problem by going from a descriptive, labor-intensive way of telling the computer what a human looks like to instead saying, you're just going to learn by, here's a bunch of examples. But it's not learning really, it's building statistical information to say, that thing looks more like a human than the other things I know about, so I'm going to conclude it's a human. And that's the primary application. Now, you can use AI for a lot of other stuff, But that's the reason it had to go into cars, is because if you want your cameras especially to know what's in front of you, machine learning is really the only technology we have that's going to get that done for you.
So essentially, it is the pattern matching that allowed people to leverage the power of AI to have those sensors recognize what's in front of you
Right.
or what's inside of you.
It's the object classification, object detection. That's the reason it has to be in cars. Now, once it's there, you could use it for a bunch of other stuff, but that's the reason they said we're going to have to bite the bullet and put these big GPUs inside cars, despite the cost, despite the power. If you want, if you want, if you want self-driving for real, not just lane following, simple lane following, you're going to need to use machine learning.
So what other application have they figured out? Okay, now that we got this big GPU and we think we kind of licked this pattern matching thing, what other applications can I use AI in my automotive? I mean, vehicles.
Inside the vehicle, you can use it for literally the entire driving task. So there are folks doing what is called end-to-end machine learning. And the way it works is camera goes in one end and steering and brakes come out the other end. And so
Okay.
it's doing the entire driving task. And so there are things, there are steps. If you're using the somewhat older machine learning, which some people still use, there's different steps. There's pull in the cameras and figure out what you're looking at and compare cameras and say, oh yeah, those two cameras are looking at the same thing from slightly different angles. And that LiDAR, those bumps on the LiDAR probably correspond to this thing I see in the camera. So there's also this sensor fusion, but at the end comes, oh, there's a pedestrian 25 meters away, standing this way. So that's one piece of machine learning you can have. But another piece you can have is here's all the things on the road. Are they going to hit each other? How do I not hit anything? And you can use machine learning for that. You can also machine learning on the side for prediction about, well, the pedestrian's there now, but where are they going to be in a few seconds? Because
That's hard.
yeah, it's hard, but machine learning can do a pretty good job at that. Now the catch is pretty good isn't the same as perfect, right? But a pretty good job at that. We can come back to that. And another one is, well, you have this plan. I want to do a trajectory and I want to take the curve without flipping the car over and without losing traction. And machine learning can do that too. So you can do that all as pieces of machine learning, but the end-to-end machine learning guys say, you know what? It's just one chunk of machine learning. Although inside it is multiple attention heads, it gets complicated. But you can, in principle, convert the entire driving task over to one ginormous machine learning chunk. And people are doing that on the road now. So my understanding is this is how current Tesla FSD works. So that's a
Right.
thing that's on the road.
Yeah. Okay.
When you say
So
ginormous, it kind of gets my attention because intuitively it seems like that is an unbelievably huge training problem and demanding of an enormous amount of compute power. So I can sort of envision the trunk being filled just the cooling. Is
Uh,
it really practical, or are we talking about something that will never be more than a test bed?
well, Tesla's running it. I keep hearing how they don't really have as much compute as they really want or need, but it's out there on the road. The Waymos of the world are the last I heard running the older kind with different chunks put together. But you can put it out. It's a significant amount of compute. Electric vehicles handy because you got a giant battery next to it. I mean, it's feasible. I suspect all the players who are on the road are right at really pressed up against the limits of their compute. But the nice thing about compute is if it's not fast enough, wait a couple years and that'll get fixed. So I don't worry about that too much because chips keep getting more capable. It isn't quite faster as much as more parallelism and more processing power. We're just sort of done with clock speed scale up, but it's more processing power. So that trend, they're in a good enough place that that's not really what's holding them back.
okay. So let's go to the heart of the matter because what gets interesting is actually the application of AI in vehicle is that this is the occasion where we can learn how AI meets human, whether it's a human drivers or the human environment, the pedestrians, the cyclists, or whoever. I mean, this is where literally that machine meets human physical environment. What have we seen so far?
So let's first do driver, then do environment, because they're completely
Okay.
different discussions, okay?
Okay.
But I don't want to lose. They're both important. All right. The driver issue, so you have automated driving, and it doesn't have to be a robotaxi to have this machine learning. Anything that uses a camera to figure out what's going on is going to have machine learning to figure out, oh, so I'm seeing this image, what is it? And some of the things are pretty straightforward, some are hard. Like a picture of a person on the side of a bus, is that a person? Is it a picture? You only have as a camera. And if you don't have a lot of good context about that's a bus and that's where the sign should be, so I'm going to go with picture, right? And there have been notable failures. There have been notable failures of that exact type, all right? So it's really hard. But what happens is you have a person driving the car. Okay, so this is an automated driving system, but not a robotaxi. So think
Okay.
of the brand names are Autopilot and Super Cruise and Blue Cruise, and a lot of the cars just have generic lane keeping, right? And they're all using machine learning to sense the outside environment of varying levels of sophistication. But when you get a high-end one that is really trying to drive the car entirely, and you're just sort of there to watch it, so the higher end, the Autopilot, the FSDs, the Blue Cruise, the Super Cruise, the whatever, there's lots of other brands, but those are the ones people may have heard of. When you're there, we've known, I've been doing self-driving car safety for almost 30 years. At the beginning, other people told me we've already figured out that people are going to have trouble paying attention when you take away steering. We've known that for a long time. And so the interaction with a human is that supervising automation is a much different task than being the automation. It's a different skill set. Uh, we have reason to believe that not everyone is good at that. Some
Right.
people are really bad at it. When you talk to the folks who are running training courses for robotaxi testing, surprisingly good drivers fail out of the tester course. And
Uh,
and it's because it's a different skill set. And there you go, right? It's different. So a different task. So a driver license does not automatically qualify you to be a supervisor, it turns out. And it's really hard to pay attention. We've known since the 1940s that people have trouble paying attention for more than a half hour to something boring.
I
And
see.
so now you put this person in there. They don't
Yeah.
necessarily have the skills. We know they're not good. We know that nobody is good at paying attention. This isn't a lack of moral fiber. It's being human. We've known this for forever. All right. So you're getting people in these cars, asking them to pay attention to something boring, which people are spectacularly bad at, and then blaming them when the car does something crazy and tries to kill them, sometimes, occasionally, sadly, sometimes succeeding, blaming them for lacking moral fiber because they were asked to pay attention for 2 or 3 hours and we know they can only do it for 30 minutes. I mean, that's kind of where we are. And so driver monitoring, it isn't just driver monitoring. If you had good driver monitoring, it would every 30 minutes tell you it's time to take a rest. Now, maybe there's driver attention management, like they can do things to wake you back up or shake you out of your rut or make the task less stressful or less boring, trying to kill you on occasion. That's an interesting concept. I personally would prefer not to, but the fact is, if it tries to kill you every 5 minutes, you're probably not going to get bored. So this is a very nonlinear dynamic. I'm having a little fun with this, but I'm kind of serious. It's a very
Yeah.
nonlinear dynamic. It's a very, very tricky problem that if you're not well staffed with people who understand human interface, you're not going to get it right. Right. So that's sort of the problem is how do you keep their attention? And also for
Right.
other road users, anyone who's driven has seen people make mistakes. And if you've driven for more than 10 years and never made a mistake, I just don't believe you, right? It's like,
Yeah.
that's just, what do people do? They make mistakes. That's just what people do. But the roads
Yeah.
are amazingly safe because we're also really good at saying, oh, that guy's going to make a mistake. That guy's going to blow the light. I think I'm not going to enter the intersection. People aren't perfect at it, but they're remarkably good. I mean, the reason you don't see a wrecked car in every intersection in the city is largely because some people are compensating for other people's mistakes.
So the thing is that the way that humans actually compensate, kind of guess that this guy, who's driving in front of me now, he looks like he's driving certain vehicle and he's an asshole. I'm going to be really careful not to, get close or something.
Or he's a bozo, or he's probably drunk. I've seen that. Yeah, this guy looks drunk. I think I'll leave some distance. Yeah, I was
Right, but that's a nuance that's something that AI driver, computer driver would be able to eventually, you
It
know,
should be, it should be able to. Now the question is, how good is it at it? Because what you're doing is you're building so you have to, these things have to build a model of the world. But
yes,
to really get to the last, past 99% down into the point oh whatever, where safety lives out. Machine learning is statistical, it's good at the average case. Safety lives in the atypical case. You're actually building a model of what's inside other people's heads. That's the only way to predict behavior that is good enough for real safety. So, as an example, you're driving down the street and a bus pulls up. So, I live in a city, and so we have a bus system, right? A bus pulls up on the other side of the street, and the light is green for you, but the bus is about to load drivers on the corner. You're going through a corner, the bus is on the far opposite corner, loading passengers, I mean. And there's a guy on your side who's looking really, really anxious and antsy at the sidewalk, at the crosswalk. What happens next? And by the way, it's 8:30 a.m. It's, peak rush to go downtown. What happens next is he runs in front of you. So I'm already on
exactly.
the brakes.
Yeah,
But if you don't have that robust a contextual model, you're not going to get that right.
right.
Now, there's a simpler one that's in every driver manual, which is you're near a playground and a ball runs into the middle of the road. What happens next, right? But at a playground, it's a no-brainer. Just jam on the brakes because you
Yeah.
know something bad's about to happen, right? And the question is the machine learning trained with a robust enough contextual model? If they're just saying, I'm just looking at what's in the road and I'm only going to stop if there's something in front of me, you're going to get that wrong. Okay, so we actually saw this happen with a cruise robotaxi pedestrian dragging mishap, that it was unaware of the context of a pedestrian being hit one lane over. And so it was not prepared for the pedestrian to appear in its lane, which is a common thing. I've personally seen that happen. This is a thing that happens all the time. And it was like, well, it's not in my lane. It's not my problem. And if you have that limited contextual awareness, you're not going to get stuff like this right.
Wow, that's a good one, actually. It's hard.
So
It's
context
context
matters a
matters.
huge amount.
Yeah,
And for sure, we've seen some companies do poorly at that.
yeah, yeah. Okay.
Okay.
So let's talk about the environmental stuff that
The environmental stuff. All right. So another reason you have to use machine learning, which sort of goes to the first one, is that it's an open world environment. So if you look at functional safety, the classic IEC 62158, ISO 26262, pick your favorite safety standard, functional safety, right?
yeah,
The model is the world is perfect except for a list of failure modes we understand, like over temperature or over voltage or loss of power or whatever, okay? And we perfectly characterize the world. We've perfectly characterized all the possible failure modes inside our equipment, but a little bit oversimplified, all the faults are inside our system. The external world isn't a problem. Any fault, anything that goes wrong is inside our system. A component breaks or a power supply goes bad or a computer fails or gives the wrong answer, right? And the outside world affects us a little bit, but we're looking very much inward, okay? And then when you do that, you get functional safety, and we're pretty good at that. We've known how to do that for a long time. So if you're willing to spend the resource and time, you're going to get that right. And what changes when you put a camera on is that a camera builds a model of the external world. The whole point is you have this camera and it's building a model of the external world. But the model of the external world will have two problems. One is it will be imperfect because it'll be an approximation of the external world. And if there are things in the external world that you're not trained on, you're not going to know what they are, and you're not going to know that you don't know what they are. Right? So it'd be approximate in terms of measurement error, but also be approximate in terms of your internal world model does not have the concept of a pedestrian being hit in the lane next to you. It's just not a thing. So back to the cruise robotaxi mishap, they saw the other car, the human-driven car, their
yeah,
trajectory. It saw the pedestrian trajectory. If you were to plot those out on graph paper, they would intersect, but it did not have the concept of that being a crash. It just assumed it would pass through, I guess, right? It did not understand that that necessarily means that they've collided. So it just lacked that from the world model. The issue with the environment is the environment contains a lot of rare events, okay? And how do you train on rare events? Well, if they're somewhat rare, you just build up a lot of data collection miles till you see them. But there's some events that will be so rare, you're not going to see them during testing and training, right? And so the people toss about the idea of long tail and edge case and all this stuff. Let me try and be a little rigorous about that, and then I can explain why it's a problem. Long tail means either if you have a distribution of things, right? That down at the end, there's very, very few things. So it's called the long tail. This happens once every million miles, once every 100 million, once every billion, right? Well, if it happens once every billion miles, you're not going to see it during training. You're just not. I mean, with very low probability, you're not going to see it. Okay. And so when the machine learning sees it in the real world, it's not trained on it. So you're rolling the dice to see what happens, right? And maybe it's trained on something sufficiently close it gets right. Maybe it's not. Maybe it gets lucky. Maybe it doesn't. And now that's not necessarily a problem on its own, because if you're safe enough, which doesn't have to be perfect, maybe that's okay. But the reason it's tricky is there's excellent reason to believe that's also a thing called a heavy tail. All right. No, long tail is rare events, but a heavy tail means there's a lot of things. So maybe this is once per billion miles. But if you have a billion of them, you're going to see one every mile. And if you fix it, that doesn't help you because there's 999 million plus, left left you haven't
It's
seen
sort of
and you
like a
haven't fixed.
guacamole effect.
Yeah,
Right.
yeah. So the thing that has been really the technical challenge is how to deal with a heavy tail situation, and how heavy is it, and how do you deal with that? And we've seen Waymo took how many years to get out on the road? And one simple way to explain it is it just took them a long time to dig through the heavy tail to the point that the surprises were arriving seldom enough and were benign enough that they felt okay going on the road. But every company is going to have to do that, and it's hard to have a shortcut. There are shortcuts, but that's the issue. So the technical problem with the environment is the rare events. Now, how does that affect safety? Well, safety is all about low probability, high severity events. Okay, so machine learning is all about the typical stuff.
Yes.
Where typical means if it's rare, get more miles until you have enough samples that you've figured it out. All right. But if you have something once per billion miles and you have 100 million miles of data, the answer is you've never seen it, probably, most likely, right? And so how do you train on stuff that you've never seen? And the answer is maybe use simulation, maybe use a large language model approach to synthesize. There's a bunch of ways to do it. But the core issue with safety is all the evidence we have thus far suggests strongly that to get acceptable safety, you're going to have to dig really far into rare events. And how do you do that if you can't just drive around and watch them happen? That's the core challenge.
That's daunting, actually. Yeah.
Yeah, well, bring $100 billion and see how it turns out, because that's where we are, right?
That's what we are doing, right?
Well, and let me comment on that, because this is important. I talk about challenges because someone has to, and the industry doesn't talk about them as much as they should. But we have robotaxis running around multiple cities providing rides. That's amazing. I mean, I've been at this almost 30 years, and 30 years ago, that wasn't going to happen anytime soon, but we're there. And a lot of that was using machine learning with fast CPUs. That was the magic key that unlocked all this. And it's just amazing technology. It's super impressive. But where you end up is, this is one of those, there's the 90-10 rule and the 99-1 rule. So where we are is, and I'm going to have a little fun with this, but the first 99% of the problem is getting the robotaxis out there in the tens or maybe a couple hundred, right? That's the first 99%. And what people have to appreciate is that that's the first 99%. Turns out there's another 99%, which is getting up to 1 million vehicles with all the scaling issues and logistics issues and heavy tail issues and all the other things that matter. It feels like we're almost there because we have a few robotaxis, but anyone's really serious about product development knows that the cool demo is not 99% done of the way to the product. There's all the other stuff you have to do too. And it feels like we're almost there, but in fact, we're just on the first step of the productization road, which is also a really long journey. It's going to take a long time. People don't want to hear it. They want their investments to pay off in 2 or 3, 4 years. And this is a multi-decade journey.
Good point.
I guess that raises another interesting question for me. If we were talking about functional safety verification or verification of an IC design, we would have tools to produce metrics to say how far along are we in exploring that heavy tail. And we'd have some idea of how much farther we have to go and what kind of risk we're taking. Are there any ways of quantifying where we are with this problem?
Sure, you can have a safety case and you can assess the safety case to UL 4600 and you can quantify the degree to which the safety case is complete and supported by evidence. And some companies are trying to take that approach. But the important thing is testing does not get you there. So in IC design, people are used to saying, well, we're at 99 point whatever 9% test coverage, we're going to go for it, right? And I used to be an IC designer, so I've been there, I've done that, okay? And there's manufacturing tests where you have to test all the gates. Stuck at fault model was cute. It's a little more sophisticated now, but ultimately, if you exercise all the gates, all the gates are there, right? But if you exercise all the neurons in an artificial neural network, it doesn't prove anything because it's the weighting. The weightings are what they are, but it doesn't mean it's going to work properly. So what's really going on with IC design is you know what it's supposed to do, and you design tests that are matched to what it's supposed to do. So there's people call it the V model, right? You have the V model in all the safety, and people misunderstand the V unless they think really hard about it. So the V model is you go from requirements to design to implementation, and then you do unit test, and you do system and integration test, and then you do system tests, right? But you don't test everything. So in an IC design, do you really test all possible 128-bit numbers multiplied by all possible 128-bit numbers? No, of course you don't, because you would never get done with that, all right? So if you're testing out a multiplier or a divider, Intel famously got that one wrong a while ago, right? What do? Well, you say, I know the division algorithm and I know the properties, and I'm going to test the properties are met, but I don't have to test every combination of numbers because I know how carry bits work and I know how these partial multiple cans work. I know the algorithm, so I'm going to test I know the algorithm is sound. I'm going to test the algorithm was implemented properly, which is different than testing all possible numbers, right? So testing is not there to test it into submission. Testing is there to prove that what you got was what you thought you were trying to design. So the left side is what you're trying to design, and the right side is what you got, and you want to make sure they match. Right? When you have machine learning, you can have a bunch of requirements. Here's the requirements for my car. Cool. And I collected a bunch of data, and the machine learning learned whatever it did. Did the machine learning learn what I wanted it to? I don't know. Let's drive it around and find out. And you've lost the causal relationship between the design and the implementation. They're completely unrelated. Other than on a good day, you have scenarios, you made sure to collect training data from every scenario. So that's people trying to stitch up that gap. But in principle, there's this huge gap. And the question is, what's your plan? How do you close that gap? And a scenario-based one is one way to do it, although there's, that doesn't get all the way there. So the validation is tough because you have machine learning that does what it does for whatever reason that we don't know.
Yeah.
And how do you prove that safe? Well, either you do brute force testing, which that's a billion miles, and you've probably retrained the machine learning 100 times in that billion miles, so none of it counts really, not quite, right? It's very, very hard to make that case. Or you somehow trace the machine learning back to the design, which is also hard. So from a design verification point of view, that's the challenge.
The tracing thing seems fascinating, since kind of by definition, you have no idea what the meaning of any of those nodes in the network is. Is there any way of going from a failure back to a root cause, or do you simply have to retrain?
So if you have a failure, retrain. There are people working on trying to reverse engineering the neural net to hypothesize why it might have failed or come up with explainability. But the problem is, as you pointed out, the machine learning does not learn in the same concepts we learn. So a lot of the explanations are just sort of telling a story, how the leopard got its spots, right? It's kind of telling a story like that. And even the ones that do it in real time, some folks are trying to say, well, we have this AI, this machine learning that explains what it's doing, and we run the explanation to a safety checker to check the actions. But you have to be very careful when you train that it doesn't get just trained to lie to the safety checker to tell it what it wants to hear, right? And I'm not saying you would do that on purpose, but machine learning is notorious for gaming the criteria, just absolutely notorious for this. So when you're a safety person, you look at this stuff and say, yeah, but what if it's lying to you? And how do you know? And the answer, well, we ran a lot of tests. Like, did you run enough tests to prove it never lies? Because remember, we're worried about once per 100 million miles. That's not very, it only has to lie that often to kill someone. Uh, that's the kind of question to ask.
It's interesting. All right, let's get back to the end-to-end stuff that
Sure.
yeah, because you mentioned something in the very beginning of there when you talked about the approach that Tesla is taking versus approach that Waymo is taking, and the end-to-end discussion came in. Tell us.
Right now, there's two different ways to look at machine learning in chunks or end to end. And it sort of maps on to the question in a really interesting way. It maps on the question about whether you want LiDAR or not. So in the self-driving car business, people say, oh, LiDAR is really important, and oh, LiDAR is just irrelevant. It's a distraction. But it's not actually about LiDAR versus not LiDAR. It's about how folks are trying to train their system. And so if you have a lot of cars on the road, so Tesla has a lot of cars on the road, and LiDARs until recently were very expensive and they're still not cheap. And so if you want to put a LiDAR in every single Tesla and it doesn't do any good except provide you with training data, that's a huge expense. Okay, you're putting a lot of LiDARs on the road to collect data. And so a different way to go is to say, no, we're going to use cameras only because they have cameras and we can get the data cheaply that way. And on the other hand, you have the Waymos of the world who built a simulation and built a closed test course, and they get all their data that way. And they can afford to have expensive sensors like LiDARs because they don't have that many vehicles. So it's not, compared to the engineering costs, the LiDARs are free compared to the engineering cost, right? If you only have 100 vehicles instead of a million, right? So one way to go is to get lots and lots of lower quality data. And a different way to go is a much smaller amount of very high quality data. All right, so there's two roads here, and neither one is right or wrong. They're just different choices. Now that couples with the machine learning kind of approach. The older approaches were chunks of machine learning, a chunk for perception, a chunk for planning, a chunk, and maybe some of it was conventional code, and there's conventional code gluing it together because, well, what about right turn on red? Well, you can write that in conventional code. But trying to teach it machine learning is sort of hard because it has to know what that particular city's rules are and a bunch of other stuff. It's a lot easier to just say, no, you're New York City, you're not allowed to do it, right? You can write the rules down and then use machine learning for the things you don't know how to write down. That's sort of the Waymo, but all the older approaches are that way. And to do that, you need machine learning training data on things like here's a stop sign, here's a yield sign. You only need to train on specific chunks of the problem. And we'll train separately on trajectory planning. We'll train separately on this other thing, right? So it's a much more manageable machine learning approach, but it requires a lot of human effort to glue it together. But that human effort provides opportunities for teaching special cases that are hard to infer but easy to explain. So that's kind of the Waymo and a lot of other folks that,
Right.
and until recently, almost everyone was there. But a few years ago, the transformer and large language model type technology came out. It's been gathering steam. And the last few years, several companies, including Tesla, but others, have switched over to that. And so that's end-to-end machine learning. Instead of a bunch of chunks with conventional code gluing them together, you have one giant machine learning system. And I understand there's some structure inside, but we're not going to go there, okay? It's a giant machine learning system. And you feed it a bunch of camera images and tell it whether it's driving the right way. And just do that over and over, and it figures out how to drive, okay? And so it's building internal structures, and you give it hints. Maybe you give it hints about, you're going to want this concept of object detection. And so here's a thing that knows what object detection is inside it, but it's still all machine learning. It's still training itself, and you give it some structure to be sure, but it's end-to-end. So training looks like feed it a bunch of images, tell it what a human driver did, and whack it on the snout with a rolled up newspaper if it gets it wrong. And it'll, this is, nope, bad dog, right? And it says, well, try again. Nope, well, not as bad a dog. Try again. Oh, good dog. Okay, it's done. I'm having fun with this, obviously, but that's it. That's end-to-end machine learning. Now, the reason you might like it is there's very, very little human effort in the training. You're not writing all this glue code. It's just figuring out. Now, to be sure, there is some hard work you have to do, but it doesn't look like writing millions of lines of C code and stick it in there. It looks like something else, okay? But you need a lot more data, because instead of saying, hey, I'm going to teach you what a stop sign is, by the way, here's a stop sign. Yes, that was a stop sign. That was not. That one is that one. So you're spending money on labelers. End-to-end machine learning, the only label is good dog, bad dog, did you drive right? So you're not spending money telling it what a stop sign is. It figures out stop signness out of context from the human driver always seem to stop. Must be this red thing, It figures that out on its own. Statistically, there's a red thing of about this shape. Guess I should stop when I see that. That's kind of what it's doing, okay? In end-to-end machine learning, you need a ton of data because it doesn't have any clues about context or pulling things or any of that. You need way, way, way more data. So you're feeding thousands and thousands of driving hours into this thing for it to learn how to drive, okay?
Is there really any hope of it actually capturing that long tail? Or will
Well,
that always lead to surprises?
opinions vary, okay? I don't think you can capture the long tail by getting road data, okay? You might be able to capture a long tail by using a simulator that knows about the long tail. And so another piece of this is, where do you get your training data for end-to-end? And back to the different strategies, if you have 1 million cars on the road, you can assert without proof that you will see the long tail because you have 1 million cars. Tesla's doing that. We're going to see how it turns out, right? But they're not in that many weird crashes, because even 1 million cars isn't that much for a once in a billion mile. I mean, you're going to see a lot of stuff. But Ron, you asked earlier about what about catastrophic crashes? Well, those take a long time to happen. It's still hard to train on those. Now, maybe you go out to a test track. Maybe you have a simulator and you do some simulation training, but inevitably everyone gets pulled into simulation for the stuff that's hard to find in the real world, or the stuff that is so dangerous you don't really want to do it on purpose, all right? And so you can build your own simulator, which the conventional guys have their own simulator that's written. Some of the folks use video game simulators. Those have a problem because they're about whether it looks good, not whether it's realistic. But you can start with a video game simulator or whatever, and then build a simulator and train that way. And those only get the rare cases if you program them in. If your simulator does not know what a kangaroo is, you're not going to get kangaroos, and they're not going to spontaneously appear out of thin air. And I use that example because Volvo famously had a trouble with that back when they tested in Australia. But it isn't just kangaroos. There's an infinite variety of those things, some of which are going to matter. So you have to spend a lot of effort building the models, even if the simulator automates a lot of the testing. But now and the chip designers know all about this, right? Well, you don't have to design the chip, but you have to design the tools that design the chip, and it's still a lot of effort. So the other thing that's been going on is that companies have been using large language models and this is oversimplified, to build the simulation for them. But they're not actually building the simulation for them. What they'll do is they'll say, here's a still image, from a camera.
Yeah.
What happens next? And the LLM will predict a sequence of several seconds worth of images that happen next. And they say, what happens next if it suddenly starts raining? And what happens next if the other guy turns left instead of going straight? And if they have enough images that are kind of similar, they can sort of interpolate, this is what this image will look like with the guy turning left, because I've seen so many left turns. And this isn't the same car, but statistically, I'm going to build you an image that scores the same on left turnedness as all the other images I have that I know are left turns. So some of the companies, Wabi, for example, is really vocal about this, that they're building their simulations using generative AI, so they don't have to build the simulation by hand. And the claim is, and we're going to see, we don't know, the claim is that because it's built on a foundation model, it has already heard about enough of the edge cases to matter, and it can bake them in, even though it's never seen data from them.
So
Where did the foundational model come from?
Well, from scouring the internet and potentially, questionably training on sources of questionable intellectual property.
I'm not sure I'm
Movements.
reassured by knowing that the model was trained on all those hours and hours of Russian dash cam footage.
Yeah,
Or
well,
Chinese dash cam, yeah.
yeah. Well, it's trained on dash cam footage. Well, but it isn't training. The thing is, the simulator isn't training how to drive on that footage. It's training how to make a model on that
Mhm.
footage.
Ah,
So the dash cam has seen something weird. The assertion is, if the dash cam has seen something weird, it's going to show up. That weirdness is going to show up in your synthetic data. And
It
some,
almost seems like there's a kind of mysticism condensing around large language models that make is bridging the gap between what they actually do and general intelligence.
well, some people are pretty careful about this. The car companies I've all looked at, or not talked to some, looked at the others. All the ones I've talked to are usually being pretty respectful of reality in this. They're not making mystical claims that I've ever seen. But when you ask them, well, so how you're using large language models and your claim is that it will somehow interpolate all the edge cases and put them in there, how's that working out? And you get silence in return. So we don't know how that's going to work out. And some people will say, well, but if you hook it up to the internet large language model, it'll figure out what a kangaroo is and just stick it in there for you. And that is very unclear how that's going to work. But the nice thing about this is it's not going to the point that it requires the generative AI to understand anything. So they're not making the claim that it understands something. They're just making the claim that if it's seen enough data and the data encompasses enough to be acceptably safe, it will successfully interpolate all the combinations and it'll work out. That's the claim. Now, I have an opinion on large language model versus conventional, okay?
go ahead.
My opinion is that conventional machine learning is kind of hard to get working for typical stuff because you have to write all this manually done glue code to get, before you get
Right.
anything, it's a lot of work. But if you notice something weird, it's not so bad writing a manual rule to handle it. It's like, oh, we're in Hawaii. Blue stop signs are a thing. Add blue stop sign to the training data, but you don't have to train the trajectory planner because a stop sign's a stop sign, right? Whereas end-to-end learning, if you discover an exception, you have to retrain the whole thing. And now when you go to Hawaii, there's blue stop signs in parking lots there, it turns out, okay? So now you have to somehow get it to understand that blue stop signs are the same as red stop signs without it necessarily knowing what a stop sign really is, right? So you're gonna have to get a whole bunch of training data from Hawaii for it to learn this concept instead of saying, no, the color doesn't matter, it's cool, don't worry, right? So you haven't changed the need to handle the exceptions, but you've converted it from a programming job of a few lines of code into a data collection job of finding enough examples of that thing to put into the data to get it trained. The thing about end-to-end is you have to appreciate how much data it takes to train. So do the math on a 5 megapixel camera times 1,000 hours times 10,000 hours at 30 frames per second. Just do the math. And yeah, there's compression, but it only gets you so much, right? It's a lot of data, and all that data has to be fed through the training system many, many, many times to train. So that's why you hear companies building supercomputers to do end-to-end machine learning. I mean, they needed a lot of, for chunks of machine learning, it was hard, but end-to-end is just a whole nother scale. And it gets down to the point of how do you feed that much data into the supercomputer quickly enough to actually compute training while you're still alive, right? And then you say, well, then it comes down to for end-to-end, the edge case question for end-to-end is, can you find enough things to put boundaries around the edge cases so you can interpolate and get everything you need? Can you get that data? And how big is it? Because if it's too big, you can't train on it. So now you need a lot of manual effort to collapse the data down to the smallest size that will successfully train. And so you're seeing a lot of effort. You're not seeing effort going into writing lines of code. You're seeing effort going into curating the data set. And so the limit is, can they get a small enough set of data curated well enough that all the edge cases are inside it and still have it small enough to train on? And that's where that ends up.
It seems like there's kind of a dilemma there that if you need edge cases far enough apart that you can interpolate everything between them, aren't those going to be the catastrophic cases that you never want to see?
Well, maybe, but the LLM is supposed to simulate this for you. I don't know. It's like, in principle, you might be able to pull it off, but it remains to be seen how that's going to go. So that's sort of the big question. The question for the conventional stuff is how you collect enough data or build your simulators to have enough edge cases to train on. And it's more mental effort about what the edge case is. And the large language models are supposed to not have that, but actually converts it from a programming exercise and a simulation exercise into a data collection and data curation exercise. The edge cases didn't go away. They just got swept under a different corner of the carpet.
Interesting. All right. Before I let you go, Phil, I want you to talk a little bit about the embodied AI. Is that the new book coming out?
Oh, that's embodied AI is the new hotness. Yeah.
Yes. Tell me
Okay.
how you define that, and then tell me about your book briefly.
So it's embedded system that uses machine learning. And I'm writing a book about it, which is the attempt is to take what we've learned from robotaxis about safety and extend it, extrapolate it to general principles that can apply to more than robotaxis. So there's a lot of robotaxi examples, but a lot of it is reflecting, well, what does this really mean for everyone else? And at the end, it says, here's what we know, and here's a long list of problems that if you're building one of these, you ought to think about because they've already burned the robotaxi guys. Don't you get burned too. Learn the lesson and make sure you have a plan, which might be, well, just don't build something like that looks quite like that. Build something else that avoids the problem, or it might be a countermeasure, or it might, who knows what the countermeasure is. But if you don't know what the problems are, you're going to make the same mistakes and learn the lessons the same hard way.
Very good. Well, thanks for coming to the show. I really learned a lot. This was a very in-depth conversation, as far as I could tell, about really different types of AI models and how people are applying them in different ways. Very educational. Thank you so much, Phil.
Well, thanks for having me on. I really enjoyed the conversation.
ARM is the industry's highest performing and most power efficient compute platform with unmatched scale that touches relation. Together with the world's largest computing ecosystem and 22 million software developers, ARM is building the future of AI.